Hey guys, the objectives for this video is to calculate the stress increase under a uniformly loaded circular foundation. So in the next couple of videos we're going to be looking at different shapes, very basic foundations, and seeing how their shape and the stress that they're under is going to cause a vertical stress increase at a particular point under the surface of the soil. So let's do a quick example. Say we have our profile of soil like this, and we have a circular base on top of it. Okay, so this is in section. This would be in plan. It would look like this. So there's our circle. So in section we have a circular base which is uniformly loaded. So let's say that the pressure or the stress that it exhibits is 100 kPa. So it's a uniform stress that it puts onto the soil. Let's say that we are looking at a point A, which is perfectly under the center line of the circle, and a point B, which is, say, 10 meters away from the center line of the soil. Let's say that this depth was 5 meters, and let's say that the diameter of our circle is 10 meters. So what we're going to be doing now is we're going to find a way to find how this circular foundation is going to increase the stress at A and increase the stress at B, and we're going to find our value of stress increase. So the first thing we need to do is define a couple parameters. So the first thing we're going to define is Z. Z is the distance from the surface to our point of interest. So in our case, Z would be 5 meters. A is the radius of the circle. So if we were looking plan, that would be A. And R is the distance from the center of the circle. So it's a little bit counterintuitive. You'd think R would be the radius and A would be this other definition, but it's not, so just remove that. So R is any point we're looking at, which is either inside, outside, or anywhere from our circle. So R is just the distance from the center of our circle. So we're going to be using these definitions, and the last definition is P equals the pressure, or the stress, the uniform stress, and we will call change in Z equals the stress increase. Okay, it's very important, stress increase, and you'll see why later on in this video. It's not just the stress, it's the stress increase. So let's do a quick example. We want to know, let's do point A. Okay, we want to know what's going on at point A. So this is point A. So we're going to define all these things. Z is the distance, so Z is 5 meters. A is the radius of the circle, so the diameter is 10 meters, which means the radius is 5 meters. And R is the distance from the center line that we're at. So in our case, we're actually 0 meters from the center line. We're at the center line, so the distance we're going out from the center line is 0. So that's 0 meters. Now what we're going to be doing is we're going to be using this graph, which is an influence graph. It looks like this. And it plots Z on A against I, which we're going to be talking about in a sec. And all these values, you should be able to see values at 10, 9, 8, 7, 6, 5. All these values are R on A. So what we need to do is we need to find Z on A, R on A, and then we can find I. So let's do that. So Z on A would equal 5 on 5, which is 1. R on A would equal 0 on 5, which is 0. So we have 1 and 0. So Z on A is this axis, and R on A is the values on the curve. So Z on A is 1, so that would roughly be around here. Here's 0 and 2, so that would be 1. R on A, which is the value, which are all these values, and we have R of A, which are all these values. We have an R of A of 0. So in our case, they're decreasing from 10 down to 1.25, and the last curve here is 0. So we'd come all the way across that last curve. So if I do this in red, so we have 1.0, which is our Z on A we found. If we come all the way across to the last curve, which is around there, and we come up, we get a value Now this is in log scale, so this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So we get a value, an I value of 0.7. So we write down that I value. I equals 0.7. Now it says here that I equals the change in Z on the pressure. So in other words, this equals the change in Z, the change in the vertical stress, over the pressure. And the pressure or the stress was 100 kPa, so over 100, which means that change in sigma Z, so change in the vertical stress, is 0.7 times 100, which is 70 kPa. So because of our foundation, which is putting 100 kPa of pressure on the surface of the soil at a point A, which is 5 meters below the surface and right at the center line, the vertical stress increase is 70 kPa. So let's do this now for point B, which is eccentric to the center line. So point B, so point B, Z is still 5 meters. A is still 5 meters. So Z and A aren't changing. The only thing that's changing is R, which is now 10 meters. We're 10 meters away from the center of our circle. So Z is still 5 meters. The depot out is still 5 meters. A, the radius, doesn't change. It's still 5 meters. But R is now 10 meters. So we can find our critical values, which are Z on A, which will equal 5 on 5, which equals 1.0. So that's not changing. And then we could also find R on A, which is our other important value, which is 10 on 5, which is 2.0, so 2 meters. We would then, just like before, come to our graph, this influence factor graph. So now we're at 1.0 and 2. So we come across, so Z on A is 1 and R on A is 2. So we're still at 1. So 1, and now we'd look for the value 2, which is there. So it says 2. So we'd come across and see where that intersects, and then we'd just go and find our I value. Once again, this is a log scale, so this is going to be 0.01, 0.02, 0.03, and 0.04. So our I value is 0.04. We know the I value is equal to the change in stress over the pressure. So the change in stress will equal 0.04. And our pressure doesn't change as well. Our pressure is still 100 kPa. So 100 kPa would give us 4 kPa. So 0.04 times 100 is 4 kPa. So look at the difference in the value. For this one, at point A, we got 70 kPa. So at point A, we're getting a 70 kPa increase. And at point B, we're getting a 4 kPa increase, which makes sense, right? Point B is quite a lot out from point A, which is right under the center of the circle. So the further we go out, the smaller the change in vertical stress is.